Okay, so hello everyone. Let us continue our discussion on density operators. So the last time we had left off at property 3, which I had referred to as gamma, which is a test on the pureness of a quantum system. And how is this test performed? You take a trace of rho square, the density operator square, and if it is equal to 1, you have a pure state, and if it is less than 1, you have, sorry, a mixed state. And this proof is quite trivial and is left as an exercise for the viewer. So that's where we left off with the last class. But a quick summary would be that if we consider any observable A, which belongs to some Hilbert space H, which we had used in the previous class, yes, and then you have a quantum system, psi of t, which belongs to this Hilbert space, then the expectation value of this observable can be calculated using uh, this, the standard method, but in the density operator formalism, this would involve a trace, which is just the trace of the observable with the density operator. And this result holds good for pure or mixed quantum systems. So the selling point behind the use of density operators was to effectively calculate the expectation values of observables, to effectively calculate the expectation value of observables in mixed quantum systems. So in mixed quantum systems, you have it's also known as it's like a statistical ensemble. So you have a distribution of pure quantum states in your system. So you have to weight these pure quantum systems or these pure quantum states with some probability factors. So in that case, for these mixed quantum systems, your density operator reads as follows. Pk, the state vector describing the quantum system, and its Hermitian conjugate. Okay. Right. So this was the main reason behind us introducing density operators. Now, an important question because we want to study spectroscopic systems. So as such, you want to study the interaction of light fields with matter systems and study the response of these matter systems to the incident light fields. And that gives you a lot of information on the dynamics of the system. The energy transfer, and so on and so forth. System path coupling as such. So you want to study these spectroscopic systems and how is the density operator useful in this scenario? As I had previously described, if you consider a sample, let's just consider this cuvette where your sample is contained. Let's just say your sample is contained within it, and then your sample is a mixed quantum state. So even if you consider electronic spectroscopy, at room temperature, in general, your system is a pure quantum system because it exists only in the ground state. And when you consider vibrational spectroscopy, your system, before any light fields are incident on it, exist in general, unless the vibrational energy gap is too large, should exist in a distribution of quantum systems. So it should be a mixed quantum system. So, as such, these mixed quantum systems predominantly exist in these spectroscopic ensembles. So, then once the light fields are incident on your sample, let's just say that three light fields incident on your sample, because this would be an example of multidimensional spectroscopy, specifically 2D spectroscopy. So, you have these two pump pulses and a probe pulse, which is incident on your sample or your matter system. So once your light fields are incident on the sample, even if you consider electronic spectroscopy, at that point your system exists as a mixed quantum system. So because let's just say if you consider a two-level electronic system with a ground electronic state and an excited electronic state, after your first light field interacts with the population in the ground electronic state, your system, your residual quantum system exists in a superposition of the ground and excited electronic state. So let's just say I would want to describe the quantum system at some arbitrary time after a light field is incident on a sample. It would be some coefficient times your ground electronic state plus some coefficient times your excited electronic state. And as I described in the previous class, this would mean that it's in a coherent state. So it's essentially in the density matrix formalism terms, it would be described by an off diagonal term, which are the coherences. But let's not digress into that right now. What I'm trying to highlight here is that the importance of these mixed quantum states in spectroscopy is very high. And to calculate spectroscopic observables in these mixed quantum systems, the density operator will be extremely useful. And that was the idea behind the previous class to introduce the density operator and to introduce its importance in calculating observables in mixed quantum systems. So, this will be extremely useful in spectroscopy. So, if you consider linear absorption spectroscopy like UV-Vis spectroscopy as such, you have only one light field which interacts with your system. So let's just say you have cuvette. These are just very simple examples and must not be taken too seriously. But let's just say you have your cuvette. I meant the illustrations. Please don't take it too seriously. So you have a light field which interacts with your sample, and this would be an example of linear spectroscopy. And in this case, the response of your sample to the incident light field will also be linear. And now, if you consider nonlinear spectroscopy, where you have your sample and then you have more than one light field interacting with your sample, then that would classify as non-linear spectroscopy. Okay, so a word of caution here that sometimes when you have a single light field which is incident on your sample, but the intensity of the light field is extremely strong. Like let's just say you whack the samples, you whack the light's intensity to a really high value. In that case, even when you have a single light field, it can produce nonlinear effects, and then you do start deviating into your nonlinear regime. So the linear spectroscopy, which I discuss here with one light field, is limited to light fields which are not that intense to generate nonlinearity effects. So that was one word of caution. So in our work, we will be limiting our discussion to nonlinear spectroscopy. And in this lecture series, we would be focusing on 2D optical spectroscopy. So in this case, you have, as I previously described, you have two pump pulses and a probe pulse. So for this sort of nonlinear spectroscopy, it would classify under third order nonlinear optical spectroscopy. So this is what we are going to study specifically. And these are also known as four wave mixing processes. And the reason behind that is quite simple. You consider the three incident light fields to be three waves, and the emitted light field, let's just say this. This is just an illustration, again, not to be taken seriously. So this emitted light field would be considered as the fourth wave. So that's why it is known as a four-wave mixing process as well. So these two words can be used to describe a 2D optical spectroscopic experiment. So it's a third order nonlinear spectroscopic technique as well as a four wave mixing process. So we will use these density operators. Let me use this to calculate this third order response. So that's the idea behind using density operators. And now in spectroscopy, the observable. So in the previous lecture, I was just using some arbitrary observable called A hat T, if you recall. So in spectroscopy, this observable is essentially your dipole operator, which I shall represent as a vector operator. Because these dipoles have a particular vectorial component as well. So I refer to it as this dipole operator. So what you measure in a nonlinear spectroscopic experiment or a linear spectroscopic experiment is known as the polarization. So this is what you see on your computer screens when you study a linear absorption spectra, your nonlinear spectra after certain data processing. So this polarization is given by the expectation value of the dipole operator. So this is what you want to calculate. And for a mixed quantum system, using the density operator would be the easiest way to calculate these polarization signals. In our case, since we're doing nonlinear spectroscopy, specifically this third order nonlinear spectroscopy, we will be calculating the third order polarization signal. So we can achieve all of this using the density operator formalism, which has just been introduced to you guys in the previous lecture. So now that we have given this introduction, let us return to the study of density operators. So in the previous lecture, I had introduced to you guys the properties of density operators, how to calculate expectation values of observables, and so on and so forth. So in this lecture, we will study the equation of motion of the density operator. Some of you must be familiar with this. This is the Liouville-Von Neumann equation. Liouville-Von Neumann. There is a dash somewhere in his name, I don't exactly recall. Uh, Equation. So, if you consider, let me describe some analogies first. So, if you consider your, your state vector, let's just say psi of t in your Hilbert space, which describes a quantum system in that Hilbert space. So, in this case, the equation of motion of this psi of t is described by the time-dependent Schrodinger equation, which is given by the partial derivative of this wave function, not wave function, state vector, I h bar Hamiltonian acting on this state vector. So now, analogously, for your density operator, you should have an equation of motion, which is your Liouville-Von Neumann equation. And as you will see, it will take on the form dou over dou t of rho hat t is equal to minus I over h bar, the commutator of the Hamiltonian with the density operator. So our task one would be to derive this equation. So let's do that. So now the density operator. Let's just consider the density operator for the mixed quantum system. So, okay, so now if you consider the evolution of the quantum system and its Hermitian conjugate to be brought about by a specific time evolution operator, let's just call it u hat t, then we can describe this time evolved quantum system as follows. And then this is just your quantum system at t naught or 0. So t naught is when you essentially start your experiment or the initial time. So in our case, we will just be using 0 as the initial time and not t naught. So this is your time evolution operator, I call it TEO, for this particular quantum system. And this time evolution operator is driven by the Hamiltonian H. So in this case, I will assume that the time evolution operator, uh, the Hamiltonian within the time evolution operator depends on time. So in the previous lecture, I had made this simplifying approximation that your Hamiltonian is just time independent H0. But in this case, my Hamiltonian is not time independent. This is quite obvious to think about because when we consider spectroscopy, the interaction of your light fields with your matter system will depend on the time when your light fields interact with your system. So in this case, your Hamiltonian will not be time independent. So the Hamiltonian, for now, we can consider it to be time dependent, but in general, you can describe it by a zeroth order component and some perturbation. So this is in general known as your matter Hamiltonian, and it describes the energies of your matter system. And then this is your perturbation, which will be the light matter interaction, and we will put in the form of the perturbation after we work out the maths. Okay, so in that case, I'm not specifying the form of this time evolution operator just yet. So in that case, what you get is rho hat t is equal to u hat t sum over k p k sin k blah, sin k u hat dagger t. So now we take a derivative of this equation. So dou by dou t of psi of t, and sorry, this would just be rho hat, which is the time independent, the density operator at time zero. So which can be mentioned as just rho hat or rho hat at time zero, but we can just stick to rho hat. So you take the derivative of the first term, get dou by dou t of the time evolution operator. So you get rho hat, you had that t plus you had t rho hat, the derivative of you had dagger t. So you're stuck here. So how do we evaluate these terms? So these terms are evaluated from the time-dependent Schrodinger equation. So you have your time-dependent Schrodinger equation, get psi of t is equal to minus I over h bar Hamiltonian psi of t. So this gives you this equation for the time evolution operators. U hat t is equal to minus I over h bar Hamiltonian thing on U hat t. So this is the corresponding operator Schrodinger equation for the essentially for the time evolution operator. So we can take the Hermitian conjugate of this expression, and that would give us u hat dagger t is equal to I upon h bar. And if you take the Hermitian conjugate of two observables, their order is exchanged. So you get u hat dagger t times the Hamiltonian, which is a Hermitian operator. So you do not need to take its Hermitian conjugate. So you will substitute this here and the Hermitian conjugate of the time evolution operator here, and then you will get your result. So dou over dou t rho hat t is equal to minus I over h bar, the Hamiltonian times u hat t rho u hat dagger t plus u hat t rho, sorry, that will be plus I upon h bar times u hat dagger t h. So here it would have been better for me to write h as h of t to carefully symbolize the dependence of the Hamiltonian on time. So I will do that just so that we are careful. So put h of t everywhere. That would be good. Okay, so this term here is just rho hat t, and this term here is also rho hat t. So what do you get from here? Dou over dou t, rho hat t is equal to minus I over h bar, the commutator of the Hamiltonian with the density operator. And this is what we set out to prove in the beginning. So, just a word of caution again, I apologize for this mistake. In general, the Hamiltonian is time dependent. So, this is your Liouville-Von Neumann equation, and we have proven it here. So that is good. So now that you have proven the equation of motion for the density operator, now we can go and look for analytical solutions for the density operator itself. So once you have an equation of motion, you can solve this equation of motion to look for the density operator at any time t. So how would we do this? Let's integrate the solution and see what happens. So you move the dou t to the right hand side and then you integrate both the equations. So we will integrate from 0 to t. So we assume that the evolution of the density operator starts at time 0 and we measure to time t. So you get a rho at time t is equal to rho at time 0, which till now we have been ignoring the index 0. So we can proceed to do that. But for now, over here, I will put in a 0 just so that it avoids confusion. Plus minus I over h bar, the integral from 0 to t, the Hamiltonian, the density operator, the tau. So we have, let's just say, think of it as integrating over a smooth function, but this is just an operator. But as an example, think of integrating a smooth function from some arbitrary time 0 to time t. So the variable of integration chosen here is tau. So tau runs over this entire time duration. So tau lies from 0 to t, can lie anywhere between 0 to t. So we have to mention the bound within which these integration variables lie every time we do this integration. So now I would want to iteratively solve this equation. What does that mean? Resubstitute rho hat tau into this equation. So rho hat tau would again be rho hat 0 minus I over h bar 0 to, let's just say, tau prime. Hamiltonian tau prime, rho hat tau prime, t tau prime. So in this case, what we are doing is we are integrating from 0 to tau. So tau prime lies somewhere between 0 to tau and integrates over this region in time. So I can rewrite this as 0 greater than prime. Tau prime is less than equal to tau, which is less than equal to t. So this would be this condition now. And now I will go and substitute rho hat tau back here, which would give us rho hat t equal to rho hat 0 minus I over h bar 0 to t Hamiltonian at time tau rho hat 0 d tau plus minus I over h bar square 0 to t d tau 0 to tau d tau prime. You have the Hamiltonian at tau with the commutator of Hamiltonian at tau prime, uh, rho tau prime. So this is what you get at this situation. And then you can proceed to do this iterative procedure over and over again. Uh, let's just say an infinitely large number of times, and then you get this solution. Rho hat t is equal to rho hat 0 plus sum from n equal to 1 to infinity. So I'm just going to write down the nth term here. Minus I over h bar to n to the power n, integration from 0 to t, t tau, 0 to tau. Okay, here I'm going to use the bit of a different integration variables. I'm going to use different integration variables, and I'll explain to you the ordering of the integration variables once I write the terms. T tau n, 0 to tau, t tau n minus 1, so on and so forth, 0 to, sorry, it's tau n, then 0 to tau 2, d tau 1, and then you have your commutator term, where in this case, by observing the trend, you can write down your commutators, the nested commutators. Hamiltonian tau n, Hamiltonian tau n minus 1, so on and so forth, to Hamiltonian tau 2, comma, Hamiltonian tau 1, rho 0. Then you close all of these up, so on and so forth. So this would be your nth order term. But there is one specific issue with the series solution which we have just crafted out here. This is the series solution to the Liouville-Von Neumann equation, where the Hamiltonian considered is a time-dependent Hamiltonian and just takes on the form Hamiltonian at time t. So there has been no separation of the time-independent and the time-dependent Hamiltonian components as of now. So when you observe this solution, which is the series solution, you can see that as the number of terms in the series go up, the number of Hamiltonians considered in each of these terms as the series terms increases. So for your first order term, you have one Hamiltonian in the consideration. For the second order term, you have two Hamiltonians, and for your nth order term, you have n Hamiltonians. And if these Hamiltonians are large, as in the energies of your matter system and your perturbation. So in this case, you are considering your matter system as well as your perturbation. So in such a scenario, your Hamiltonians are destined to be really large because the energies of the matter system have been considered in full detail, and these are the major contributors to your Hamiltonian. So if this is also considered in the series, this series will diverge because the nth order term will have n Hamiltonians and the n minus 1th term will have n minus 1 Hamiltonians. So as the series grows larger and larger, it will diverge. And as a consequence of this divergence, you cannot truncate this series. Now, this is an issue. So, you need to figure out a way in which you can find a solution by truncating this series. So, when you consider third order non-linear spectroscopy as such, or in general, nth order nonlinear spectroscopy. You have n perturbations or n interactions of the matter system with the light field. So if you consider third order nonlinear spectroscopy, you have three interactions of the light field of the matter system with the light field. So in this case, if I was considering solving the third order nonlinear spectroscopy problem, I would have to consider n equal to 3 term from our series. So higher order terms must not be considered and the third order term would be considered in this case. So because you only have three light matter interactions. So you want to derive a series which converges and then you want to pick out only the third order term from that series to calculate your third order nonlinear response. So in that case, you are accounting for the three light matter interactions and you are getting your response of your system to the three light matter interactions using time dependent perturbation theory. So, how can we do so? You use the interaction picture. So, what motivates this? Okay, so what motivates the interaction picture, the use of the interaction picture is that we want to derive a similar series as that shown above in V. So as you have seen above, the series which we have derived is in terms of the full Hamiltonian. But if we consider only the perturbations which are V, we can truncate this series and a solution exists because then your series would converge. And the rationale behind that is that if you consider your Hamiltonian as a function of time, the matter Hamiltonian is the large component of the Hamiltonian. The perturbations are just small. So the light matter interactions are very small compared to the matter system. So what I need to do is I need to figure out a way in which I can get rid of this matter system from this series and then create a series just in terms of these perturbations, truncate the series, and then reintroduce this matter system Hamiltonian. And then, in a sense, I can construct the full solution. So let's write down a plan. One, separate out H0 from the series solution and derive a series in terms of the perturbation. Number two, select out the third order non-linear term which contains three light matter interactions, or generally just perturbations, because this framework can be used outside spectroscopy too. But yeah, but we want to focus on the light matter interactions. Yeah. So you select out the third order nonlinear term which contains the three light matter interactions. Then what you do is you reintroduce the evolution with respect to the time independent matter Hamiltonian. And then by doing so, you construct a full solution. And the reason behind doing that is you want a solution which converges and which does not diverge. So, to operate in this interaction picture, what we need to do is consider your density operator again. We are going to consider the density operator of the mixed quantum system. K, psi k p, ra, psi k p. So as of now here, what we have been doing is we consider the time evolution operator for the state vector and another time evolution operator for the Hermitian conjugate of the state vector. So now what I will do is I will consider a time evolution operator with respect to the zeroth order Hamiltonian only. And by doing so, I'm pulling out the evolution of the quantum system with respect to the matter Hamiltonian. So consider the time evolution operator with respect to the matter system given as such, and of course it will take on the form exponential minus I over h bar h0 t. So this evolves the quantum system with respect to the zeroth order Hamiltonian from time 0 to time t. And then your density operator reads as follows. It will be u hat 0 t sum over all k pk get psi k t in the interaction picture. Right now I'm putting the I on top because there's a K already. Otherwise, in general, the I is mentioned at the bottom itself. Ra psi I T U hat dagger T. So why does this classify as the interaction picture, and the reasoning behind using it has been described previously, but what I want to do here is just partition out the evolution with respect to the matter system. So what is left is that your system, your resultant system, evolves only with respect to your perturbation or your interaction Hamiltonian. It evolves with respect to v of t. So by partitioning out your matter system, there is a certain component of your system which is being evolved with respect to time evolution operators, and then there is certain component of your system which we will evolve by constructing your Liouville-Von Neumann equation with respect to the perturbations, right? So as a consequence of which you're operating somewhere in between your Heisenberg picture and your Schrodinger picture, And that's why this is known as the interaction picture. It's an intermediate picture. And please don't misinterpret the words interaction picture with respect with perturbation or interaction Hamiltonian. When I use the word interaction Hamiltonian, it is specific to the light matter interaction. And then this interaction picture is just quantum mechanical, and it is used to specify a picture which is in between the Heisenberg picture and the Schrodinger picture. So I hope that is clear. And now I can refer to this quantity as the density operator in the interaction picture. So I will call it rho hat IT. So your rho hat T is just U hat 0 T rho hat IT U hat 0 dagger T, which, if you recall, is very similar to what I showed you guys in the previous class, which is rho hat T equal to U hat 0 T rho hat U hat 0 dagger T. And this was the case where your Hamiltonian is time independent. But when your Hamiltonian is time dependent, you get this. So this, which we derived in the previous class and showed, is just a simplification to the more complicated case we are considering here. So I hope that is clear. So continue with our, sorry, let's continue with our discussion with this. So now what we want to do is derive. So we repeat the same procedure as we did in the previous case because we want to calculate the density operator using this interaction picture. So now what we want to do is derive the Liouville-Von Neumann equation for the evolution of the density operator in the interaction picture. So for rho hat I t. So what I will do is I will bring this equation down and write it in terms of rho hat it. So rho hat it will just be u hat dagger t rho hat t u hat t as such, because what I could do is apply u hat dagger t here, u hat dagger t with respect to the zeroth order Hamiltonian, and apply it here, and then apply u hat t here and u hat t here, and then I get this result. So this equation is in terms of the interaction density operator written in terms of the full density operator. So now let's just proceed to take a derivative, but here you have to be very careful because there's three terms that are dependent on time. So you take a partial derivative of the density operator in the interaction picture. You take a derivative of the first term. Just to recall, this is just the time evolution operator with respect to the time independent matter Hamiltonian. So it would just take on the form of a simple exponential, right? So you take the derivative of the first term, and this would have a Hermitian conjugate, so it would be plus I upon h bar. So you take derivative of the first term, you get this times the next two terms, and correspondingly you do this for the other two terms, where you take a derivative with respect to the second term, and likewise you take a derivative for the third term, which is going to be, so this is what you get. Just to remind you guys that since this time evolution operator is defined in terms of the zeroth order Hamiltonian itself, it will commute with the zeroth the matter Hamiltonian. So the commutator of this would be zero. So they're compatible observables, and we can interchange their orders, which we should do. So let's consider the first and third terms in the right-hand side of the equation I have presented above. T is equal to I upon h bar, h0 times this is just rho hat I t from above minus I upon h bar times you have u hat dagger t rho t u hat t, which is again rho hat it h0. So essentially, the first and third term is just a commutator of the matter's Hamiltonian with the density operator in the interaction picture. Now, how do we deal with the second term, which is quite critical, is we refer to the Liouville-Von Neumann equation for the evolution of the full density operator. So that would give us, if you recall, minus I over h bar Hamiltonian at time t rho hat t. And then this Hamiltonian at time t would just be in this case, right? So we put this in. So we write down the equation again. We write it as a commutator of h0 with rho it plus u hat dagger t times minus I over h bar times, we split the commutator now with respect to h0 and v. So we can write h0 rho hat t times u hat 0 of t. And then you will have another term u hat t minus I over h bar times v of t rho hat t rho hat t. Sorry, this will not have this Hermitian conjugate. So it looks like this. Now, if you observe very clearly in the case of the second term, this u hat dagger t and this u hat t can be brought inside here because they commute with the Hamiltonian h0, and then u hat dagger t rho t u hat t is just rho it. So what this term effectively will give you is minus I upon h bar h0 rho hat it. And that will go on to cancel the first term in the derivative. So the first and second terms will cancel each other out. So what you resultantly get is this is equal to minus I upon h bar u hat 0 dagger t times the commutator of v of t rho hat t u hat 0 t. Okay, so we proceed to expand this commutator. U hat v of t rho hat t u hat 0 t minus the other term from the commutator. Will still have the u hat v rho hat t v hat t u hat 0 t. So you get this. Now, what I am going to do here, which is really interesting, is that I will insert here u hat 0 t, u hat 0 dagger t, which is a unitary operator. So this holds, it's just an identity. And I will do the same here. I will insert u hat 0 t, u hat 0 dagger t. So what you end up getting here will be something which is quite interesting. So what you end up getting here is minus I upon h bar. You had dagger t, vt, you had t, which I shall call the the perturbation in the interaction picture, which if you notice, I put the I at the bottom now. So from now, I put the I at the bottom. In the previous case, I put the I at the top because they had another label K, which was put at the bottom. But in general, we put I at the bottom. Times U hat dagger T, rho T, U hat T is again the density operator in the interaction picture as considered minus the density operator in the interaction picture, VIT. Now, just to recall, this perturbation in the interaction picture has been defined as such. It has been defined as U hat dagger T with respect to the matter Hamiltonian or the zeroth order Hamiltonian, V of T, U hat T. So this is how we define the perturbation in the interaction picture. And you, as if you recall, any observable in the interaction picture is defined as such. You had dagger T with respect to the matter system, the observable, and you had 0t with respect to, I already mentioned the zero, but with respect to the matter system. And again, if the perturbation, if the observable itself is independent of time, it simplifies things a lot because then this interaction just gets replaced with your Heisenberg operator, and then this is independent of time. So I hope that clarifies that. But yeah, so this is how we define. If that wasn't very clear, you just define this as the perturbation in the interaction picture, and it is defined as such. So now you have your Liouville-Von Neumann equation in the interaction picture, which is very good. It only depends on the perturbations and is independent of the matter system, the H0. So we have successfully partitioned out the large part of the Hamiltonian, which contains the energies of the matter system and was preventing the series solution from converging. So now when we do the integration, we will get a series solution which converges, and then we can reintroduce the matter system evolution in time by introducing these zeroth order time evolution operators once we find the series solution. So this is what we intend on doing. VIT rho IT. Right. So now we proceed with our discussion. And just to recall, let us list down everything which we have uh, defined. VIT from right above is you had 0t, we had t, dagger, you had 0t, and then I'm going to write this in terms of rho of t. It's just you had 0t, rho it, you had 0 dagger t. So good. So these are the two things which we have, equations which we have generated by moving into the interaction picture. So now let us solve this by integrating again and taking the dou t on the other side of the equation and integrating both sides of the equation. So rho hat it will be equal to rho hat I p naught plus or I can just directly write minus I over h bar 0 to t tau v hat I tau rho hat I tau as such. And what I could do after this would generate a solution for rho hat I tau and iteratively plug it in, which would be rho hat I. Sorry, I'm not using the T naught label, I'm using 0. So rho hat I 0 minus I over h bar 0 to tau t tau prime, where tau prime lies between 0 and tau. We had I tau prime, rho hat I tau prime. And now this can be reintroduced here. So what we end up getting is rho hat I t is equal to rho hat I 0 minus I over h bar 0 to t tau v hat I tau rho hat I 0 plus minus I upon h bar square 0 to t tau 0 to tau d tau prime v hat I tau and then comma the commutator of v hat I tau prime with rho I 0. This is the second order term, and then you proceed so on and so forth. Now, something which we should discuss clearly is you can drop the label on rho hat I 0. Why would that be? Going back to the definition of rho hat I t, which is just your u hat 0 tagger t rho hat t u hat 0 t. So at time equal to 0, this would just be rho hat I 0 is these will just be identity operators because there's no evolution in time. So you're just rho 0. So you can drop this I everywhere. Yes, I apologize. This is not 0. That is not a good mistake to make. This would be tau prime here, not 0. And then you continue with this solution and you calculate the solution for you do this iterative procedure an infinite number of times and you will get a series solution which looks like this. Rho hat it is equal to rho hat I uh, t naught or 0, but I drop the I, so rho hat 0 plus sum over n from 1 to infinity minus I over h bar to the n, and then you integrate from, let's say, 0 to t tau n, 0 to tau n, t tau n minus 1, so on and so forth, to 0 to tau 2 t tau 1. Again, in the previous case too, I changed the integration variables to tau n minus 1, and I didn't describe the way they are ordered. I apologize for that, but I will take care of it here so that we are careful with the order of integration of our variables. Yes, so then you get the nested commutator where you have the perturbation in the interaction picture at tau n, along with the commutator of the perturbation in the interaction picture at tau n minus 1, and then you take the commutator of the perturbation in the interaction picture at tau n minus 2, blah, 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 blah. Let's just write down the last term here, which would be the perturbation in the interaction picture, tau 2 with the commutator of the perturbation in the interaction picture at tau 1 along with the density operator at 0. So you close this, close this. So this is what you get, and this is your nth order term. And now, if you think about it, if your perturbations are considered to be small enough, your solution will converge. And what we are specifically looking for here, as I previously mentioned, is your third order density operator term in the interaction picture, because we want to consider only the term where there are three light matter interactions. So I will consider the third order term for the purpose of our 2D spectroscopy study, and that would be equal to minus I upon h bar to the power 3, 0 to t d tau 3, 0 to tau 3 t tau 2, and 0 to tau 2 t tau 1, and then your perturbation. So your perturbation in the interaction picture at tau 3, your perturbation in the interaction picture at tau 2, and then your perturbation in the interaction picture at tau 1, along with rho at time 0. Okay, so before I proceed, as I promised, the time ordering of the variables. So if we consider some smooth curve which has to be integrated from 0 to t, and our first variable of integration is tau n. So if tau n runs over this entire area, then you are integrating this curve. Next, you consider tau n minus 1, which lies between 0 and tau n. So tau n minus 1 integrates from here to here. So tau n minus 1 will be placed somewhere here. And then you consider tau n minus 2, which integrates from 0 to tau n minus 1. So tau n minus 2 will be placed somewhere here. So you get the ordering of variables, and it is quite easy to think about that t is greater than equal to tau n, which is greater than equal to tau n minus 1, which is greater than equal to tau n minus 2, so on and so forth, which is greater than equal to tau 2, which is greater than equal to tau 1, which is greater than equal to time 0. So this is how you order your variables. Likewise, in this case, your t is greater than equal to tau 3, which is greater than equal to tau 2, which is greater than equal to tau 1, and which is greater than equal to 0. So this is how your integration variables will be arranged in this case. So this is your third order density operator in the interaction picture. And now what I would like to do is to introduce the form of the perturbation which is considered in a spectroscopy experiment. But before I do so, what I would like to do is also go back to the rho of t. How would I do that? So to go back to the third order density operator term, I would have to apply a u hat 0 t to the density, third order density operator in the interaction picture, and the Hermitian conjugate of the time evolution operator with respect to the matter system. So I can construct the third order density operator term as such: minus I over h bar cube, you put in u hat 0 t, and then the triple integral 0 to t d tau 3, 0 to tau 3, d tau 2, 0 to tau 2, d tau 1, and then the nested commutator I tau 3, vi tau 2 vi tau 1 with rho 0. So you have three commutators here, which are within each other. So this is your third order density operator term, which will go a long way in calculating the expectation value of the dipole operator, which is the key quantity which you measure in a spectroscopy experiment. Now, something interesting is that we have to do a little bit of the transformation of variables here, which will help a lot to physically understand this third order density operator term physically. So its physical interpretation will be easier, and then the understanding of the interpretation of the expectation of the dipole operator will also be easier. So that would be a good thing to do. So what we will do is, before I explain that, as of now, the way the integration is considered is if I draw a time axis and then you have three perturbations at tau 1, tau 2, and tau 3. So this is 0. Let's just say you have tau 1, tau 2, and tau 3. So your density operator from time z. Okay, let me not get into the physical interpretation of it before fully deriving the math. That would not be correct. Let me just say for now that you have three interactions or three perturbations. One is at tau 1, one is at tau 2, and one is at tau 3. So what I would like to do is to set this first perturbation here at tau 1 to 0. So I want the first perturbation to be incident on the system at 0, and I would like to describe the subsequent perturbations as a function of the delay between the perturbations. So what do I mean? I would like to set tau 1 to 0, and then I would like to define this delay term between the perturbations and call it T1. And then this T1 would be tau 2 minus tau 1, and subsequently T2 would be tau 3 minus tau 2. I would like to do that. So by doing that, it would simplify the math quite a bit. And again, I have forgotten to mention the U hat dagger T here with respect to the matter system, but it's good to mention that in because that's a mistake. So what we have to do now is to transform the integration variables. So what I could do is set tau 1 to 0 and d tau 1 will be minus dt1 and d tau 2 will be minus d2. And of course, uh, and then you have time t. So let's call t3 as t minus tau 3. So you will get d, sorry, d tau 3 is minus dt3. So what will that give you when you do that? You get the third order density operator as minus I upon h bar cube. You will get an integral. So first you have the u hat 0 t, which is if I consider this to be t1 and this to be t2 and this to be t3, and this has been shifted to 0. So time t will just be t1 plus t2 plus t3. So I shall start using that here. T1 plus T2 plus T3. So that's our first change here. And once you work out the integration variables, you will get something which integrates from 0 to infinity. But to do that, you have to consider one more thing, which is you consider these zeros here. And notice that from minus infinity to 0, your system doesn't evolve in time. So any contributions for the integration from minus infinity to 0 will be 0. So as a mathematical trick, you can set the lower limit of these integrals to minus infinity, because the contributions towards this third order density operator term from minus infinity to 0 is 0, because there's no perturbations incident on the system. So you can consider this mathematical trick and some contributions from minus infinity to 0 as well, because by doing so, when you transform your variables, which I have described here, and reset the limits of your integral, you will get a very nice integral. So what we will get here is from 0 to infinity, you will get dt3, 0 to infinity, dt2, 0 to infinity, dt1, and then you have your perturbations in the interaction picture, which is v hat I, which will be t2 plus t1, later v hat I t1 at I0 on row 0. And of course, you have, I shall not forget at this time, the Hermitian conjugate of the time evolution operator with respect to the matter system. So this is what you get. And this simple change in your integration variables now allows for the recastation, I don't know if that's a word, of the time index as such, of the time of the variables as such. So 0, you have, let's just, how do we put this? So you have 0, you have t1, you have t1 plus t2, and then you have t1 plus t2 plus t3. So your first perturbation is at time 0, which is here. Your second perturbation is at time t1, which is here. And then your third perturbation is at time t2 plus t1, which is here. And then after that, you evolve your system with respect, which is a free propagation with respect to your matter system, to t1 plus t2 plus t3, where your signal will be read. But let's not get into that as of now, because for that, we need to calculate, not yet. So for that, we need to calculate the quantity which we have done all of this formalism for, which is the expectation of the dipole operator. So for that, let us define the form of the perturbation. So this perturbation takes on the form of the dot product of the dipole operator vector with the electric field vector. And of course, this electric field will have some direction in which it is propagating given by vector r, but for simplicity, we ignore that now. Another simplifying approximation, which is definitely not true, is that But to work out the math and for the initial understanding of these third order nonlinear optical response functions and theory and so on and so forth, you ignore the polarization of the electric field and you ignore this and the orientation of the dipoles in your ensemble or system. So you ignore this and then you ignore this. So you needn't consider the dot product. And of course, you in actuality, you would have to consider the dot product, which gives rise to polarization studies. But for now, we ignore the 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 interaction of the polarized electric fields with the ensemble of dipoles in the system, which are randomly oriented or oriented in a certain fashion. So we will just write this as a minus mu hat dot E of t. This dot is not the dot product, so I might as well get rid of it. So you write it this way, and then this is the interaction Hamiltonian. Now, how will I write the interaction Hamiltonian in the interaction picture, which is kind of funny. So this is the interaction Hamiltonian. Don't get confused between the two interactions here. This is the interaction Hamiltonian or the perturbation. And then this is the interaction picture. So this interaction picture is just quantum mechanics. The interaction Hamiltonian is just a word to describe the interaction of the light field with your matter system. So please don't get confused between the two interactions here. So this interaction Hamiltonian in the interaction picture, as I had previously described, is just U hat dagger T V T and then U hat T. Something important for you guys to also realize here is that your dipole operator is independent of time in your Schrodinger picture. So when I write down my perturbation here or my interaction Hamiltonian, I'm writing it in the Schrodinger picture where the operator doesn't evolve in time, but your system evolves in time. So essentially what happens is these transition dipole operators in the Schrodinger picture, they do not evolve in time. That's why there is no time dependence here. Only the electric field is time dependent. So please pay close attention. So the perturbation is only dependent on time because the electric field is dependent on time, not because the dipole operator is dependent on time. And that's important. So now you have the interaction Hamiltonian in the interaction picture, and then we calculate it for the light matter interaction Hamiltonian given here. So as you can observe that these quantum mechanical operators will only act on the quantum mechanical observable. So that brings us to the very important point that I'm going to bring the perturbation or the interaction Hamiltonian down, mu hat times E of t. This is defined so-called semi-classically. Now, what does that mean? The semi-classical formulation of the interaction Hamiltonian is that your dipole operator is a quantum mechanical operator, but your light field is classical. So your light field is just a classical solution of Maxwell's equations and takes on the form e raised to the power I k vector dot r vector minus omega t. So that sort of solution is what we are talking about, classical light fields. We are not talking about photons and quantum light fields here. So the dipole operator is the only quantum mechanical object here. So when I want to calculate the interaction Hamiltonian or the perturbation in the interaction picture, these time evolution operators, which are quantum mechanical, will only interact with this. The electric field is just a number to these operators because they are classical. So what I would do is I can write it this way. You had dagger T U. Okay, there'll be a minus sign, and u hat t times e of t, which is just a scalar. So the scalar can be brought to the front too. That's not a big deal. Okay, so here this is the dipole operator in the interaction picture. This is how I'm going to define the dipole operator in the interaction picture. So I will call this u hat I t, and it's just u hat dagger t u hat u hat 0 t. So this is how I define the dipole operator in the interaction picture. And just a word of caution, it is quite obvious that the dipole operator, as I previously defined in the Schrodinger picture or in the definition of the interaction Hamiltonian, or as I mentioned, the perturbation, the dipole operator is independent of time. So I needn't put this I at the bottom. So what a lot of people will do is they will drop this I because it is implicitly assumed that if the dipole operator has time dependence, it is in the interaction picture. The reason behind that is that the dipole operator is independent of time in the Schrodinger picture. So if it is independent of time in the Schrodinger picture and I put the time dependence, it automatically implies that you're in the interaction picture. So what people will do is they'll write it as u hat t instead of u hat it, and then it's the same u hat dagger t u hat u hat 0 t. So very good. So what I will get is minus mu t E T. But in actuality, you will have to take a dot product while considering the polarization of the light fields and the orientation of the dipole operators, as I had mentioned. But we are ignoring that for now. So for now, your interaction Hamiltonian in the interaction picture is just the negative product of your dipole operator with the electric field. And this again, just to remind you, I know it's quite confusing with the I and without the I, is just u hat 0 dagger t u hat u hat 0 t, and then this electric field is classical. So that's great. So now what we are going to do is we are going to substitute this vit into this equation here, and we will see what happens once we substitute the Hamiltonian, which describes the light matter interactions, into the third order density operator term. So what you end up getting by doing so is a result which must be verified and is left as an exercise for the viewer. So consider this homework, but your solution would look like this. Your third order density operator will have a positive I over h bar cube. Till now you had a negative, but now you have a positive. So this positive comes because you have three perturbations, right? So that there's three negative signs, and that gives you a negative sign which cancels out the negative sign from the previous equation. 0 to infinity dt3, 0 to infinity dt2, 0 to infinity dt1. So we are going to put in the perturbation and the electric field. Quite obviously, the electric fields can be brought out of the commutator when I put it in because they are just classical. So I will park the electric fields here, and then I will leave the the dipole operators inside. So what do I get? I get E, sorry, you get E of t minus t3 times E of t minus t3 minus t2 times E of t minus t3 minus t2 minus t1 times your u hat 0, t3 plus t2 plus t1. Then you have your u hat t2 plus t1 u hat t1, and then u hat 0, row 0. Close this, close this, close this, and then you will also have the u hat dagger t3 plus t2 plus t1. Something which is quite essential to be understood here is the reasoning behind using e of t minus t3. So as I had just mentioned, if you look at the scale and you consider, um, it would be easier to observe from here that e of t minus t3 is the same as e of t1 plus t2, and then et minus t3 minus t2 is the same as e of t1, and then e of 0 is the same as e of t minus t3 minus t2 minus t1. So let me redraw the scale so that it is a bit clear. As we consider, at time 0 you have first perturbation, at time t1 you have the second perturbation, at time t1 plus t2 you have your third perturbation, and then at time t1 plus t2 plus t3, also known as t, you are measuring your third order density operator. So if you're considering t, so this is t1, this would be t2, and then this would be t3. So E of this t minus t3, which is at this time, would be the same as E of t1 plus t2, because in actuality, when you substitute this equation into your expression, you should get E of t1 plus t2. So E of t1 plus t2 is the same as E of t minus t3. That's why this has been mentioned here. And then the next term which should be considered is E of t1. And E of t1 is the same as E of t minus t2 minus t3, or E minus t3 minus t2. E of t minus t3 minus t2. Yes, sorry. And then the last one would be E at time 0, which is from here. And E at time 0 will just be E of t minus t3 minus t2 minus t1. So this is a nice way in which we can write it. And you are measuring, just to remind you, the density operator at time t, which is after your three perturbations. Now, you want to measure the expectation of your dipole operator, which is written this way. But in our consideration, I will ignore the the vectorial component of the dipole operator and just write u hat. So you want to calculate this. Now, if you recall from our previous class, which is the entire reason behind that introduction, your expectation of any observable in a mixed quantum system will just, or a pure quantum system, would just be given by the trace of the observable with the density operator. In this case, I'm measuring the expectation of u hat, which will be given by the trace of the density operator with u hat. But in this case, I want to measure only the third order polarization signal because I want only three light fields. So I will call this, by the way, so the polarization is represented by P3T, which is the expectation of the dipole operator on considering the third order terms, or essentially only considering the three incident light fields. I'll put a tiny 3 here. I know it's an abuse of notation, but I would rather have clarity than using concrete, concise notation, precise notation. So it would be the trace of the dipole operator with the third order density matrix or operator term, which we have derived here. Uh, right here, this huge thing. So what I need to do right now is simply take a trace of this row third order term with the dipole operator. And I shall recast this and call this as the third order polarization as capital P, P3T. Again, ignoring the vectorial component, or in general, these polarizations will also have a vector here. Yep, so we're not digressing into that. Or this is the same as trace of U with the third order term. So we proceed to take the trace, which will give us the expectation, the expression for the third order polarization as such. So you have the I upon h bar cube integral from 0 to infinity dt3, integral from 0 to infinity dt2, integral from 0 to infinity dt1, and then you have the three electric fields, so the E of t minus t3, E of t minus t3 minus t2, and then E of t minus t3 minus t2 minus t1. And then, of course, these quantities needn't be traced. So you have to take a trace around all the quantum mechanical quantities. So the light fields, just to remind you one last time, are classical. So the trace of the dipole operator with you have the u hat 0, t3 plus t2 plus t1, and then you have the commutators where you have the u hat t2 plus t1, u hat t1, u hat 0 along with rho 0, or you can write rho 0 or rho minus infinity. As I mentioned to you, that the system is stationary from minus infinity to 0. So some people will write rho 0, some people will write rho minus infinity, and some people will also call this a rho equilibrium. It's because the system is in equilibrium because before any light field is incident on the system. So just a word of caution on these different notations. Then you put close the commutators, and you also have the u hat dagger t3 plus t2 plus t1. Now we shall recall a property of the trace which we learned in the previous class, that the trace is invariant to cyclic permutations. So the trace of A, B, C is the same as the trace of C, A, B. So what I will do is I will move this U hat dagger over here. So what that gives me is something very nice, and that's why I want to move that. So I get the trace of U hat dagger T3 plus T2 plus T1 U hat 0 T3 plus T2 plus T1. So I'm just writing the trace part down here. So what I'm doing is I haven't copied the rest of it yet. I'm just going to copy this over here to tell you what I'm trying to do. And then you have the nested commutators. I'm going to just denote it by this bracket for now. Right. And then this term, which I have gotten here, if you can notice, is just your dipole operator at T3 plus T2 plus T1. So it's the dipole operator in the interaction picture, but we aren't writing the I at the bottom because the dipole operator is independent of time in the Schrodinger picture, as I previously described. Because if you recall the definition of the dipole operator in the interaction picture, where I had defined to you, it's U hat at time t is equal to u hat 0 dagger at time t times mu. Sorry, not mu, not u. So the dipole operators are mu. I apologize if I said u previously. So mu. So mu at time t is u hat 0 dagger t mu u hat 0 t. So this is how I define the dipole operator in the interaction picture. So this term is just u hat t3 plus t2 plus t1 using this definition of the dipole operator in the interaction picture. So that's how you deal with these two zeroth order time evolution operators once you take the trace. So it's quite neat. The math is very nice, I suppose. So let me rewrite the third order polarization term completely now. So you get I upon h bar cube 0 to infinity dt3 0 to infinity dt2 0 to infinity dt1, and then you have e of t minus t3 e t minus t3 minus t2 e t minus t3 minus t2 minus t1. So you have the three electric fields, and then after that you have this trace, which is the trace of u mu hat t3 plus t2 plus t1, and then the commutator which contains the dipole operators, nested commutator. So I will rewrite this and then we can proceed with our derivation. Rho 0. I will still continue using rho 0. I won't go to minus infinity or equilibrium. So you have this. Now we need to make a very critical observation at this point, and the critical observation is that the first three dipole operators, which describe the interactions of the perturbations with the matter system. So it describes the interaction of the light fields with the matter system, which are these, this one, this one, and this one. And these act on the density operator, right? Which is like the interaction of the light field with your system. These are all contained within the commutator structure. You can notice that very clearly that they're all contained within the commutator structure. The fourth dipole operator here is not contained within the commutator structure. It is outside the commutator structure. And to explain the physical significance to you here, the first three dipole operators describe the interactions of the light with the matter system, and then the last dipole operator is actually the response of your matter system to the three light fields. So it is the emission of the signal field. So I would like to write down the meaning very clearly here. This dipole operator not contained within the commutator, it represents the emission of your signal field, as you would call it, emission of signal field. And then the first three dipole operators are just interactions of your light with your matter system. So I call it LM interactions. So that's important to realize. And these three electric fields here are the ones which cause these uh, interactions, right? And these are scalar electric fields, and the strength of the electric field determines the response of your system. That's why you have these three terms here. But the quantum mechanical interaction is described by these dipole operators in uh, green here. These are the interactions of the dipole operators with your matter system. So good, we have some physical intuition on what this means. And now I would like to mention that this term, the trace of u hat t3 plus t2 plus t1 with this commutator structure u hat t2 plus t1 and you had t1 and then you had 0 rho 0 is what is referred to as your third order nonlinear optical response function. So all of these derivations have led us to this point, and this is what you exactly want to derive. So this quantity here, which is multiplied with the three electric fields. So these are the three electric fields, and this is the quantity which is multiplied with the three electric fields, is your third order nonlinear optical response function. So let me write it down really clearly. Third order nonlinear optical response function. And this contains the mathematical information, as the word itself describes, on the response of the system to the light fields. So this is what you have to calculate for different matter systems to simulate your multidimensional spectra. So what we can do after this is to expand this nested commutator. So if you see this commutator, it has it's one commutator inside another. So expanding this commutator will actually give you 2 raised to the power 3 terms, which are 8 terms. So what we will do next is expand these and get the 8 terms. And then following which you can have a diagrammatic interpretation of the scenario 2, which are your double-sided Feynman diagrams. So we will discuss that in the next class. And we will also discuss on what we should be doing with these electric fields. So another thing which we will be doing is we will be using something which is known as the impulsive limit approximation. So in this impulsive limit approximation, what would happen is these electric fields would be treated as being infinitely narrow in time, such that they can be treated as Dirac delta functions or delta functions, and then as a consequence of which the integration is gotten rid of. So if we want to analytically study these solutions, what we can do firstly is get rid of this integration and focus on the third order nonlinear optical response functions. So in the next class, we will expand this commutator and proceed from there. Thank you.